Moving on in 2.4, talking about the identity function. And all this is grounded in is the principle that if I have some kind of an operation, right, whether that's addition, whether that's subtraction, in this case composition, there's usually some sort of identity element present, or identity something present. And if we're operating on functions, we should probably have an identity function. And in this case, the identity function is a function that when I compose with another function leaves that other function unchanged. So let's kind of explore this a little bit. Actually, I'll keep the same color. If we think about addition, if I just think about addition, well, the identity in addition is 0, right? Because for any number, if I add 0, it leaves that number unchanged. The same is true for subtraction. If I subtract 0, nothing changes. With multiplication, we know that 1 is our identity because multiplying, or in this case also dividing by 1, leaves that number unchanged. So what element can I compose, or what function could I compose with another function in order to leave that function unchanged? So if I think about f of g of x here, right, this is the same as saying f of g of x. And whatever I do, something has to happen so that eventually I just end up with f of x. Well, it stands to reason that if I, that's a terrible color for this case. If I need to start with g of x and find something to call g of x to get to x, well, the simplest way of doing that is just to say that g of x is x. And that is my identity function. My identity function is y equals x. So the identity for the operation of composition is the function y equals x. And that's all they say about that. That's all the book says about that. That's all I'm going to say about it. We're going to move on to inverses. So an inverse function, and hopefully you've seen this in Algebra 2, is something that when I compose it with another function, they kind of cancel out, and I result in the identity. Again, think back to what we know about other operations. Addition and subtraction are inverses. Because I know that if I have an element and I add the opposite of that element, I get the identity. If I have an element and I multiply by the reciprocal of that element, I get the identity. So I guess addition and subtraction might not have been exactly what I was going for here. Just like we had an identity for composition, we also have an inverse when we deal with functions. So I should be able to compose a function and its inverse together and get the identity. And it doesn't matter which order I do this in. You might have remembered from Algebra 2, excuse me, that to find f of x, I'm going to interchange the places of x and y and solve for y. We can check our result by composition. And we have to check our result in both directions. Right, because I want to make sure this works out both ways. So kind of a simpler example is to look at 3x minus 2. So I said the plan is to interchange x and y, just like I did here, and then solve for y. So it's going to give me x plus 2 over 3. And then we can also say that this is probably, and we'll check it in a minute, r inverse. So we're going to use this f inverse notation. So let me just push this all over here for a minute. Let me use a different color here, and I'll check our result as well. So I want to check first by composing f with f inverse. All right, so I'm going to take f of our inverse function. So I get 3 times x plus 2 over 3 is 2. Well, we know that the 3's will cancel, the 2's will cancel. I'm left with x. That looks good. We need to check this the other direction as well. So I'm going to take f inverse of 3x minus 2. So I'm going to do 3x minus 2 plus 2 over 3. And again, the 2's will cancel, the 3's will cancel, I'm left with x, I'm good to go. So if I were to graph this, if I were to graph both my functions here, so if I were to graph 3x minus 2, I'm going to have just a line, right? Let's see if I can get this right. Yeah, so just a line, right? Here's 3x minus 2. And here's its inverse. So that's 1/3 x plus 2/3 if we're trying to graph this, right? So 2, 3, something like this. I hope it works. All right, it's not going to snap, so we're going to just assume that that's a straight line. X plus 2 over 3. It's hard to see with a line. It's easier to see with other functions. But you might have noticed that there's actually some kind of a symmetry going on here. I straight up missed. All right, let's try this again. There's actually a kind of symmetry here about the line y equals x. And that is true for every function and its inverse. So kind of the key result here is that a function and its inverse are symmetrical about the line y equals x. What this also means is that if AB is on F, then BA is on F inverse. So what does this mean for domain and range? Well, normally I have a function f and it's going to take my element x and it's going to bring it to f of x in the range of f. Well, an inverse is going to undo that, right? It's going to return me to my original element. This is be the function f inverse, right? This is like squaring something and taking the square root. This is f inverse of f of x. What you might see sometimes written as f inverse of y, right? So my range of f becomes my domain of f inverse, and my domain of f becomes my range of f inverse. So you see this kind of crisscross thing going on. We have to take this one step further. Only functions that are both one-to-one and onto have inverses. These functions we call bijective, where we say that they have a one-to-one correspondence. You might be asking yourself, well, like x squared does have an inverse. Its inverse is the square root of x. Well, we have to kind of mess with the function so that it actually works. And this is something that maybe you weren't told in other math courses, because sometimes we just need to give you the simpler answer to move on for the time being. But we need to restrict the domain of a function in order to make this bijection or make this one-to-one correspondence. So here's our perfect example. I have a function that maps, theoretically, all real numbers to all real numbers. And that function is supposedly x squared minus 3. So if I graph this function x squared minus 3, I know it's going to move down 3 units, so I'm just going to eyeball it, right? It's just going to look roughly like this. Well, this is neither one-to-one nor onto. It needs to be one-to-one because of that symmetry with the reflection, right? If I were to just completely obey the reflection and do this, then my resulting function is not really a function because of the vertical line test. So we need to make sure this function is one-to-one. So in order to make this function one-to-one, I could restrict the domain in two ways, right? I could take all of the x values less than 0, or I could take all the values or equal to, or I could take all the values greater than or equal to 0. We typically prefer to take the positive option. That's typically just conventional. So I actually want, maybe I'll pick a brighter color here. I want this piece that I'm actually going to work with. So we're going to restrict my domain to all x such that x is greater than or equal to 0. We also need to restrict our codomain so that it's onto, right? This is clearly not an onto function right now because I have stuff down here that doesn't have a match. So we need to restrict our domain by making, or our codomain by making this an onto function, and we're going to do that by just limiting our codomain right where the minimum value of the function is. So we're also going to restrict our range to be y such that y is greater than or equal to -3. And so our function is actually redefined now as mapping the numbers from 0 to infinity to the numbers from -3 inclusive to infinity. And we are still obeying this rule x squared minus 3, so that can stay. Well, now I'm good, right? Now I can actually take the inverse of this function. This is where I would exchange x and y and solve for y. Now, normally when we take the square root of a number, we need to make it plus or minus, but because we've restricted our domain to just the positive values on both ends, we no longer need to make this positive or negative, right? So there's no plus or minus here because of our restrictions. So now this function has an inverse, right? This function does not have an inverse at the beginning because of our domain and codomain. Now that we've changed our domain and codomain, our function has an inverse. So now, once I've created these restrictions, our inverse function is square root of x plus 3. And that's something you could check on your own, right? I can actually draw this out so that you can see the symmetry. And now our function, our inverse is still a function now, right? If I hadn't made this restriction, my inverse wouldn't be a function. So now my inverse is a function. One last piece is that a function is a self-inverse if the inverse and the function are the same. The book tells you that one example of this is 1 over x. Obviously, the identity would be another one. I don't know of any others. And that's all the book says about it, so we're not going to really focus on it much further.